Welcome to the deep dive. This is where we take those computer science concepts you think you know, the foundational ones, and really pull them apart, see what makes them tick.
And sometimes see what makes them explode.
Exactly. Today we're doing a deep dive into something super fundamental, elegant even, but also surprisingly controversial, the linked list.
Oh, controversy is definitely the right word. If you just think of it as a sort of dynamic array, you're really missing the big picture, the important picture.
Yeah, we're going way beyond the textbook definition today.
We have to. We're talking about the core architecture, yes, but also the hidden costs, the performance traps, the clever variations people invented, because frankly, the basic version can fail pretty spectacularly on modern hardware.
So our goal here is to give you that deeper understanding. We'll cover the structure, sure, but really focus on memory, algorithms, and those trade-offs.
And it all comes down to this core idea: indirection and dynamic memory. That's what sets linked lists apart from arrays.
Right. Arrays are simple. You get a block of memory, all nice and contiguous. Element 1 is right next to element 2.
And finding element I is just math, right? Base address plus I times element size. Boom. Direct calculation. Fast.
But linked lists, they're like the abstract artists of data structures. The nodes, the individual elements, they can be scattered anywhere.
Literally anywhere the memory manager decides to put them. The only thing connecting them, the only thing creating that sequence is pointers, references, addresses.
It's a logical sequence, not a physical one.
Exactly. Arrays need that physical closeness, that contiguity for speed. Linked lists, well, they embrace fragmentation, they use pointers to stitch things together.
Flexibility.
Flexibility, but as we're about to see, that flexibility comes with a massive, often hidden performance price tag, especially when the CPU gets involved.
Okay, let's start peeling back the layers, the absolute basic building block, the node.
Right. In the simplest case, a single linked list, your node is basically just two things. You've got the actual data you want to store.
Could be anything, an integer, a string, a huge complex object.
Yep, whatever. And the second part is the pointer, the reference, usually called next. It holds the memory address of the next node in the chain.
And if next is null or points to nothing,
that's the end of the line. You've reached the tail of the list.
There's a kind of recursive beauty to it, isn't there? A list is either empty or it's one node pointing to another list.
Precisely. That recursive definition is elegant. The data can be simple, complex, even just another pointer to something else entirely. The node is just the container, the link in the chain.
Okay, elegance noted. Now for the harsh reality check. Memory allocation. This is where the fragmentation thing really comes into play, right?
Oh, yeah. This is critical because you typically allocate each node individually, maybe using malloc or new.
The memory manager just finds the first available scrap of memory that's big enough.
Exactly. Doesn't care about keeping your nodes together.
Yeah.
So node A might end up at address 0 by 1000. Node B could be miles away at 0 by 5F80. Node C might be back near the start at, 0 by 2100.
They're scattered all over the heap.
Completely scattered. And this isn't just messy housekeeping. This is the fundamental performance problem. Following the list means jumping unpredictably across memory addresses.
And modern CPUs hate unpredictable jumps. They're built for locality.
They absolutely despise it. CPUs rely heavily on caching and something called spatial locality. The idea is if you just access memory location X, you're probably going to access X plus 1 or X plus 2 very soon.
So they prefetch.
Exactly. When the CPU needs data from main memory, which is slow, it doesn't just grab the 4 or 8 bytes you asked for. It grabs a whole cache line, typically 64 bytes of surrounding data, and pulls it into its super fast cache, L1, L2.
Assuming you'll need the neighbors soon. Arrays play perfectly into this.
Perfectly. You access element 0, the cache line brings in 1 through maybe 15. Your next few accesses are lightning fast cache hits. You only get a cache miss maybe once every 16 elements or so.
But linked lists, following that next pointer.
Could jump you megabytes away in memory. Total cache miss. The CPU has to stall, wait for the slow main memory access, fetch a new 64-byte cache line for maybe just 8 bytes of pointer data.
And the stuff it fetched around that new node, probably useless because the next node is somewhere else entirely.
Precisely. Every single current.next operation is potentially a cache miss. And a cache miss isn't cheap. It can cost hundreds of CPU cycles just waiting for memory.
Hundreds of cycles per node traversal. Ouch.
Ouch is right. The hardware prefetcher, which tries to guess your next memory access, totally useless for a standard linked list. The access pattern looks random. This is why, and we'll hammer this later, an ON list traversal can be literally 10x, even 100x, slower than an ON array traversal in the real world.
Wow, okay. That really reframes the flexibility benefit.
Yeah.
So let's talk about managing this structure. There's overhead involved.
Right. At minimum, the list itself needs an entry point. That's the head pointer. It just stores the address of the very first node.
And like we said, if you lose that head pointer,
The list is gone. The nodes are still floating around in memory, unreachable. A memory leak waiting to happen if you're not using garbage collection. That single head pointer is the lifeline.
but we often add a bit more, right? For convenience or performance.
Yeah, common enhancements are adding a size field directly to the list structure. Costs a tiny bit of memory, maybe 8 bytes.
But saves you from having to walk the entire list just to find out how long it is. Makes getting the length O1 instead of ON.
Exactly. Big win. Or adding a tail pointer, which always points to the last node.
That must speed up adding elements to the end.
Dramatically. Turns ON appends into O1. Essential if you're implementing something like a queue. These are classic memory for speed trade-offs.
Okay, and then there's the hidden overhead, the cost from the memory allocator itself, especially if our nodes are small.
Yes, this is often overlooked. If you're using a general-purpose allocator like malloc in C or new in C++ alloc, that allocator has a lot of work to do for every single tiny node you request.
It's not just handing you memory, is it?
Not at all. It has to manage its internal data structures, like free lists, to track available chunks. It needs to ensure memory alignment, maybe pad your request. In multi-threaded code, it needs locking to prevent corruption.
And it adds its own metadata to each chunk.
Right. It needs to store information about the size of the block, maybe pointers for its free list, status flags. This metadata can easily be 16, maybe 24 bytes or more per allocation.
So if I'm storing a list of, say, 4-byte integers,
You could be using 16 or 24 bytes of overhead just to manage that 4 bytes of data. The overhead dwarfs the payload.
inefficient.
Hugely inefficient. The cost in memory and also the CPU time spent inside the allocator doing all that bookkeeping can completely dominate the cost of actually using the list. It's the hidden tax of dynamic allocation for small objects.
All right, let's zoom in on the simplest variant, the singly linked list, or SLL,
Yeah.
defined by that single next pointer.
Yeah, the key constraint is it's unidirectional. You can only go forward from head towards tail, no going back.
And that dictates how you interact with it. Traversal is always at current.next loop.
Always. Every algorithm has to work within that forward-only limitation. Traversal time is fundamentally ON, proportional to the number of nodes.
Which, as we just discussed, can be a slow ON because of caches. And this directly impacts random access, right?
Absolutely. There is no random access in a linked list, not in the O1 sense like an array. To get to the 100th element.
You have to follow 99 next pointers first, one by one.
Exactly. It takes OI, time, involving I pointer dereferences and potential cache misses to reach element I.
Okay, but SLLs do have strengths. Insertion and deletion at the head are super fast.
That's their killer feature, O1. Constant time. You create your new node, set its next pointer to point to the current head, and then update the head pointer to your new node. 3 simple steps. No searching involved.
Which makes them perfect for stacks, right? Last in, first out, push in and pop it from the head.
Textbook use case. Stacks are often implemented with SLLs for exactly that O1 efficiency at the top.
But adding to the tail, that's a different story. Unless you paid for that tail pointer we mentioned.
Right. Without a tail pointer, you have no shortcut. You have to start at the head and walk the entire list, node by node, until you find the one whose next is null. That's ON.
Only then can you tack on the new node.
Yep. The actual pointer update is O1, but finding the spot takes ON. Maintaining that tail pointer makes appending O1, which is crucial for efficient queues, first in, first out.
Okay, and inserting somewhere in the middle. Position I.
Similar logic. The insertion itself, rearranging the pointers, is quick, O1. But first, you have to find position I1.
Which means traversing from the head again.
Right. So the whole operation becomes OI, which can be as bad as ON if you're inserting near the end of a long list.
Now, deletion. This feels like where the SLL's one-way nature really bites. The predecessor problem.
This is the SLL's Achilles heel, absolutely. Deleting the head is easy, still O1. Just update the head pointer to head.next, done.
But deleting anything else.
You need access to the node before the one you want to delete, the predecessor.
Because the node you're targeting only knows what comes after it next.
Yeah.
It has no idea who points to it.
Exactly. Let's say you want to delete node C in a chain, A, B, C, D. You can find C, but to remove it, you need to change B's next pointer so it bypasses C and points directly to D.
And in an SLL, from C, you can't get back to B.
Nope. So, To delete C, you have to traverse from the head until you find B, the node whose next is C. That traversal makes the deletion ON.
Even deleting the tail.
Yep, still ON. You need to find the second to last node to set its next pointer to null. Even if you have a tail pointer giving you direct access to the last node, it doesn't help you find the second to last one any faster. Still gotta traverse.
That's a common gotcha. So having a tail pointer helps appending, but not tail deletion in SLL.
Correct. And if you want to delete a specific node by its value, say, find and delete the first X.
You still need its predecessor.
Right. You typically use that two-pointer technique, we'll cover more later. Keep track of previous and current as you traverse. When current finds X, you use previous to do the bypass. Previous.next at next current.next. Again, the search itself is ON.
So summing up SLLs, minimal memory overhead, just one pointer. Super fast O1 head operations. Great for stacks.
But terrible random access, no backward movement, and deletion anywhere other than the head is inefficient, ON, because you always need that predecessor.
Basically, only use them if your access pattern is strictly head-focused or simple forward iteration.
Okay.
So the SLL has some painful limits. Enter the doubly linked list, the DLL. The fix involves adding more structure, right?
Exactly. We address the SLL's biggest weakness, the predecessor problem, by adding a second pointer to the node structure.
So now each node has data, a next pointer, and a prev pointer.
Precisely. Next points forward, prev points backward. This immediately gives us bidirectional traversal. You can walk head to tail, or if you track the tail, you can walk tail to head.
And this prev pointer must unlock some serious performance gains for certain operations.
Huge gains. The most significant is deletion. Remember how deleting anything but the head in an SLL was ON because we needed the predecessor?
Yeah, that was the main headache.
In a DLL, if you have a pointer to the node you want to delete, say node N, that node already knows its predecessor, n.prev, and its successor, n.next.
Ah, so the node itself contains all the information needed to remove itself from the chain.
Exactly. It's self-contained context. To delete N, you just do two things. Tell n.prev that its new next node is n.next, and tell n.next that its new previous node is n.prev.
You essentially make them point around the node being deleted.
Yep. n.prev.next, n.next, n.next.prev, lcli.prev. 4 pointer updates total, maybe handling edge cases for head-tail. But crucially, no traversal needed, it's O1.
Constant time deletion, as long as you have a pointer to the node, that's a game changer.
Massive game changer. This is why DLLs are the backbone of structures like LRU caches.
Least recently used caches. How does the O1 deletion help there?
An LRU cache keeps track of items, usually in a list, with most recently used at the head and least recently used at the tail. When you access an item that's, say, in the middle of the list.
You need to mark it as most recently used, which means moving it to the head.
Right. And that move involves 2 steps. First, removing it from its current position in the middle. Second, inserting it at the head. With the DLL, both steps are O1. The removal is O1, thanks to the prev pointer, and insertion at the head is always O1.
If you only had an SLL, that removal from the middle would be ON, making the whole cache update slow.
Exactly. The O1 deletion of a DLL is what makes efficient LRU caches feasible. Same goes for inserting before a given node, also O1 with a DLL.
And what about deleting the tail? That was ON. In an SLL, even with a tail pointer.
Now it's O1 in a DLL, assuming you track the tail pointer. The tail pointer gives you the last node. Its prev pointer instantly gives you the second to last node. Update the second to last nodes next to null. Update the tail pointer. Done. O1.
Okay, bidirectional power, O1 deletion.
Okay.
What's the catch? There's always a catch.
Memory. We doubled the pointers. We doubled the pointer overhead.
Right. If a pointer is 8 bytes on a 64-bit system.
An SLL node had 8 bytes of pointer overhead. A DLL node has 16 bytes. Prev and next.
Back to our 4-byte integer example. Now we have 16 bytes of overhead for 4 bytes of data. That's a 400% overhead.
It is, and that can matter a lot if your nodes are small and you have millions of them.
But hang on, if the data part of my node is huge, like a megabyte image or something, then adding an extra 8 bytes for the prev pointer is basically nothing, right? Like 0.00008% overhead. Surely the flexibility always wins then. When does that 400% penalty actually hurt?
That's a really important point. You're right. If the payload is massive, the relative pointer overhead becomes negligible in terms of just memory size. The penalty hurts most when the payload is small and you have many nodes. Think about things like representing parsed text, where each node might just be a character or a token plus pointers, or maybe a list tracking lots of small events.
So it's not just total memory usage, it's about how many nodes fit in the cache.
Exactly. Even if the total memory isn't prohibitive, if half your node size is just pointers, you're fitting fewer actual data elements into each 64-byte cache line. When you traverse, you're pulling pointer-heavy cache lines, effectively wasting precious cache space and bandwidth on structure instead of substance. So the penalty is felt in cache efficiency, leading to more misses, even with large payloads if you have enough nodes.
Okay, so memory and cache efficiency. Any other costs to the DLL?
Complexity. Maintaining consistency is now harder. You have 2 pointers per link to keep synchronized.
You mean n.next.prev must always point back to n, and n.previ.next must also point to n.
Precisely. Those invariants must hold. Every time you insert or delete, you're manipulating up to 4 pointers, and you have to get all of them exactly right.
One mistake.
And you corrupt the list. You could end up with nodes that are unreachable going forward but reachable going backward, or vice versa. Or worse, you could create dangling pointers pointing to memory that's been freed. Debugging DLLs can be tricky.
So robust helper functions for insert delete are pretty much mandatory.
Highly recommended. Don't try to manipulate the pointers manually every time. Encapsulate the logic.
Okay, so SLLs and DLLs have their pros and cons, mostly centered around traversal, deletion, and memory overhead. But the core issues, like fragmentation and ON search, led people to invent more advanced list types. Let's start with circular linked lists.
Right, the idea here is simple. Get rid of the null terminator, instead of the last node's next pointer being null.
It points back to the first node, creates a loop.
Exactly, it forms a closed ring. Often you don't even store a head pointer, you store a single pointer to the last element.
Why the last one?
Because from the last element, last.next immediately gives you the first element. So you have quick access to both ends of the loop from a single pointer.
Clever. This must simplify some operations, not having to check for null.
It can. Adding to the end, which is really just before the node pointed to by last or the beginning last.next, becomes a bit more uniform. But traversal gets dangerous.
Ah, right, if you just keep following next pointers.
You loop forever. You absolutely must keep track of where you started and have a condition to stop once you've made a full circle. A do-while loop is common.
Hmm.
Do process current.next while current node.
Makes sense. What kind of real-world things map well to this circular structure?
Anything inherently cyclical. The classic example is round-robin scheduling and operating systems. You put processes in a circular queue. The scheduler gives CPU time to the current process, then just moves to the next one in the ring, wrapping around automatically.
Nice. Any others?
Circular buffers are another big one. Think streaming data, audio processing, network packets. Data comes in, fills the buffer. When it's full, new data overkits the oldest data at the beginning, effectively wrapping around.
Okay, cool. Now let's tackle that ON search problem head-on. Skip lists. These sound fascinatingly complex.
They are conceptually brilliant. It's a way to get O log n search times, like a balanced binary tree, but using a linked list structure with a probabilistic approach.
Log n search from a list.
You start with a basic, sorted, singly linked list, level 0. Then you build additional express lanes on top.
Express lanes.
Yeah. Some nodes, chosen randomly, get an additional next pointer that skips over several nodes at level 0, that's level 1. Then some of the level 1 nodes get another pointer that skips even further ahead, creating level 2, and so on.
So a node might have multiple next pointers, one for each level it participates in.
Exactly. How many levels a node participates in is determined probabilistically. Like, you flip a coin, if heads, it gets promoted to the next level up and you flip again. If tails, it stops at the current level.
Random coin flips give you logarithmic performance. That seems unlikely.
It sounds weird, but the math works out with high probability. Because higher levels skip exponentially more nodes, you end up with a structure that's effectively balanced.
Okay, so how do you search?
You start at the highest level express lane from a special head node. You traverse forward along that top level as far as you can without going past your target value.
Drop down.
Then drop down one level at the node just before you would have overshot. Repeat the process, traverse forward on this lower level, drop down again when needed. By always taking the longest possible jumps on higher levels, you skip huge chunks of the list.
Effectively narrowing down the search space exponentially, like a binary search.
Precisely. You get O log n, average search, insertion, and deletion, and the big win. Compared to balancing a complex tree like a red-black tree, inserting or deleting in a skip list involves only local pointer changes and maybe some coin flips. This makes them much easier to implement correctly in concurrent, multi-threaded environments.
Simple concurrency is a huge advantage. Where are they used?
High-performance databases, key value stores, Systems needing fast concurrent lookups where tree locking might be too complex or slow. Redis uses them, for instance.
All right, sticking with performance, let's address the cache problem directly. Unrolled linked lists. This sounds like a hybrid approach.
It is. It directly attacks that fragmentation and cache miss issue we keep talking about. The idea is to blend arrays and lists. Instead of each node holding just one data element, an unrolled list node holds a small array of elements, plus the usual single next pointer to the next node block.
So a node is like a mini array that points to the next mini array.
Exactly. And the size of that internal mini array is chosen carefully. Usually it's sized to fit snugly into one or maybe two CPU cache lines, say, 8 elements if each is 8 bytes, filling a 64-byte cache line.
So when you access the first element in that node's array,
The whole array, the whole cache line's worth of elements gets pulled into the cache. Subsequent accesses to elements 2, 3, 4, up to the end of that mini array are super fast cache hits.
you get the spatial locality benefit of an array, but within the node.
Right. You significantly reduce the number of pointer dereferences needed to traverse a given number of elements, because each jump gets you a whole block of elements. It drastically improves cache performance for sequential access compared to a standard list.
While still keeping the list flexibility for adding removing whole blocks.
Yep. You still have O1, insertion deletion of entire nodes, blocks. Of course, inserting deleting an element within a node's array might require shifting elements within that array, which has a cost, but overall cache performance is much better.
Where would you use this?
The situations where you deal with blocks of data but still need dynamic resizing. Text editors storing lines, each node holds characters of a line, some sequence representations in bioinformatics, maybe certain kinds of buffers.
Okay, one more variant, mostly a historical footnote now. XOR linked lists.
Ah, yes, the XOR list, a really clever, almost mathematical trick from a time when memory was extremely scarce.
The goal was space saving, right? Mimic a DLL with only one pointer field per node.
Exactly. Instead of storing both prev and next pointers, 16 bytes on 64-bit, the node stored just one pointer-sized field. This field held the result of prev XOR next.
XOR, the bitwise exclusive OR operation. How does that help?
Because XOR has a neat property. A XOR B implies A XOR C equals B, and B XOR C equals A. So if you are currently at node B, and you know the address of the previous node A, you can find the next node C by calculating A XOR, stored XOR value at B.
Well, okay. And similarly, if you know the next node C, you can find the previous node A by calculating C XOR, stored XOR value at B.
Precisely. You could traverse both ways, like a DLL, but using only half the pointer memory. Genius on paper.
So why don't we use them anymore? Sounds like a great optimization.
It died for several very practical reasons in modern systems. First, pointer manipulation like this often violates compiler assumptions, especially around strict aliasing rules. Compilers optimize aggressively based on assumptions about how pointers work. XORing breaks these assumptions, forcing less optimization, potentially negating the space savings with slower code.
Okay. Interacts badly with optimizers. What else?
Debugging becomes a nightmare. Debuggers expect to see actual memory addresses in pointer fields. They can't easily interpret or follow these XOR values. You can't just inspect the pointer in your debugger and see where it leads.
Impossible to trace manually.
Very difficult. And the third, and maybe biggest nail in the coffin, garbage collectors hate them. GCs work by tracing reachable objects starting from roots and following literal pointer references. They can't follow an obfuscated XORed pointer. An XOR list looks like a collection of disconnected nodes to a standard GC, leading to the whole list being prematurely collected.
So not portable, hard to debug, breaks GCs, and messes with compiler optimizations.
Yep. The marginal space savings just weren't worth the immense hassle and fragility in modern software development. A fascinating historical curiosity, though.
We've touched on memory allocation a few times, the fragmentation, the overhead. Let's really dive deep into why the way you allocate memory for list nodes matters so much. You mentioned general allocators like malloc have issues.
Big issues, especially for lists with many small nodes. The first one we discussed briefly is external fragmentation.
That's when you have lots of free memory overall, but it's all broken up into tiny, unusable pieces.
Exactly. You keep allocating and freeing small list nodes. Over time, the heap gets chopped up into small holes scattered everywhere. You might have megabytes free in total, but you can't allocate a slightly larger contiguous block because no single hole is big enough. Linked lists are prime culprits for causing this.
And distinct from that is internal fragmentation.
Right. Internal fragmentation is wasted space inside an allocated block. Maybe the allocator rounds up your request to the nearest power of 2 or adds padding for alignment. Or, as we saw, the allocator's own metadata takes up space within the block it gives you. That unused space within the allocated chunk is internal fragmentation. Lists suffer from this too.
But the real performance killer seems to be the allocation overhead itself, the time spent just asking for memory.
Absolutely. For every single malloc or new call for a tiny node, the allocator might have to search through potentially complex data structures like free lists or trees to find a suitable block, potentially acquire locks to be thread safe, perform bookkeeping updates, handle alignment. It's a lot of work.
And for a small node, that work can take way longer than actually using the node later.
Easily. The latency of the allocation-y allocation can completely dominate the useful work done with the list, especially if you're creating and destroying nodes frequently.
This sounds like a strong argument for avoiding general allocators for list nodes if performance matters. What's the alternative? Memory pools.
Memory pools, or object pools, are a classic, highly effective solution. Instead of asking the system allocator for memory for each node, you ask it for one big chunk upfront, say a megabyte.
Okay, grab a big block, then what?
Then you manage that block yourself. You carve it up into perfectly sized smaller chunks, exactly the size needed for your list node, data plus pointers. You maintain your own simple free list, linking these small chunks together within the big block.
So when you need a new node, you don't call malloc.
Nope. You just grab the first chunk off your internal free list super fast, probably just a pointer update, O1 allocation.
And freeing a node.
Same thing in reverse. Add the chunk back to the front of your internal free list, also O1.
So you bypass the slow system allocator entirely for most operations. What are the other benefits?
Big ones. First, locality. Since all your nodes are coming from that one large contiguous block, they tend to be physically closer together in memory. This helps the CPU cache. More nodes might fit in a cache line, and prefetching might actually work sometimes between nodes allocated sequentially from the pool.
Reduces the cache miss penalty we talk about.
Mitigates it, yes. Second, it eliminates external fragmentation for that node type. All your nodes live inside that pre-allocated pool block. Third, it can significantly reduce internal fragmentation because you size the chunks exactly as needed without the general allocator's overhead or rounding.
Memory pools sound like a huge win for list-heavy applications.
They are standard practice in high-performance C++ for things like game engines, network stacks, anywhere you have lots of small fixed-size objects being created and destroyed.
Okay, pools are fast. Is there anything even faster? You mentioned arena allocators.
Arenas, sometimes called bump allocators, are the absolute speed demons of allocation. But they come with a significant restriction.
How do they work?
Super simple concept. You allocate a large region of memory, the arena. You keep a single pointer, let's call it next free, initially pointing to the start of the arena. To allocate memory for a node, you just return the current next free address and then bump next free forward by the size of the node.
That's it. No free lists, no metadata, no locks.
Nothing. Just check if there's enough space left, return the pointer, and increment. It's incredibly fast, basically just pointer arithmetic. Allocation approaches O1 with an extremely small constant factor.
Okay, that sounds amazing. What's the catch? How do you free memory?
That's the catch. You don't free individual nodes. Arena allocation is designed for scenarios where you allocate a bunch of objects that all have roughly the same lifetime. When you're done with all the objects allocated in the arena,
You free the entire arena block in one go.
exactly. You just reset the next free pointer back to the beginning if you want to reuse the arena, or free the whole chunk back to the system. There's no mechanism for individual deallocation.
So perfect for temporary data structures.
Perfect. Think about building an abstract syntax tree during code compilation. You allocate lots of nodes rapidly using an arena. Once compilation is done, you just discard the entire tree and the arena it lived in. Or processing a web request, allocate all temporary objects for that request in an arena, then free the whole arena when the response is sent. Maximum speed, but only suitable when you can tie object lifetime to the arena's lifetime.
Shifting gears slightly, let's think about managed languages like Java or C#, garbage collection. How do lists interact with the GC? We know circular lists can be tricky.
Right. Simple reference counting GCs have problems with cycles. In a circular list, every node is pointed to by at least one other node in the cycle. The reference counts never drop to 0, so the collector thinks they're still live, even if the entire cycle is unreachable from the rest of the program. Leak.
So you need more sophisticated GCs.
Yes, you need tracing collectors like mark and sweep or copying collectors. These start from known roots, like global variables or the stack, and trace all reachable objects by following pointers. Anything not traced after the marking phase is garbage, including entire unreachable cycles. Modern GCs handle cycles correctly.
Does the GC add any overhead when we're just modifying the list, like changing next pointers?
It can, yes, particularly with more advanced concurrent or generational collectors. They often need to know when a pointer changes, especially if a pointer in an older memory region is made to point to an object in a newer region,
Why do they need to know that?
to track object graph changes efficiently. This tracking mechanism is often implemented using something called a write barrier. It's a small piece of code the compiler inserts automatically whenever you write to a reference field, like assigning to node.next.
So every time I do current.next equally node, there might be extra hidden GC work happening.
Potentially, yes. The write barrier code runs, updating the GC's internal bookkeeping. On its own, a write barrier is very fast, but if you're doing millions of list modifications, insertions, deletions, reordering, the cumulative overhead of all those tiny write barriers can become noticeable, slowing down your application threads, the mutator. It's another hidden cost of pointer manipulation in managed environments.
Linked lists might be slow for random access, but they've inspired some really clever algorithms. Let's talk about the two-pointer technique. You called it a Swiss Army knife.
Yeah, it kind of is. It's a general strategy where you use two pointers iterating through the list, usually at different speeds or with a fixed gap, to find something out in a single pass without needing extra storage.
The classic example is finding the middle element, right?
Yep. You have a slow pointer that moves one step at a time. Slow, slow.next. And you have a fast pointer that moves two steps at a time.
Hmm.
Fast, fast.next.next.
Because fast moves twice as fast.
When fast reaches the end of the list, slow will be pointing right at the middle element, or the first of the two middle elements if the list has an even length.
And you did it in one pass, O(n) time, without knowing the length beforehand, and only O(1) extra space for the pointers. Very neat.
Very neat indeed. Another huge application is cycle detection. Floyd's cycle finding algorithm, the tortoise, and the hare.
Same setup, slow and fast pointers.
Same setup. If there's a cycle in the list, the fast pointer will eventually enter the cycle and start looping. Since it's moving faster than the slow pointer, which will also eventually enter the cycle, the fast pointer is guaranteed to eventually lap the slow pointer.
They'll meet, point to the same node at the same time.
Exactly. If slow is fast at any point, you found a cycle. If fast reaches the end, null without the meeting, there's no cycle. Again, O(n) time and O(1) space. It's incredibly elegant.
Can we adapt this for other problems, like finding the nth element from the end of the list? That
Yeah.
sounds tricky in a singly linked list.
Yep. Another two-pointer trick. Let's say you want the fifth element from the end. You start two pointers, P1 and P2, at the head. First, advance P1 forward 5 steps.
So P1 is now 5 nodes ahead of P2.
Right. Now advance both P1 and P2 one step at a time, keeping that 5-node gap between them.
Until
P1 reaches the end of the list, its next is null. Because P2 started 5 steps behind and they move together, when P1 hits the end, P2 must be pointing at the 5th node from the end.
Brilliant. One pass, O(n) time, O(1) space again. Okay, let's talk about modifying the list structure itself. Reversing a list seems like a common task.
A very common interview question, too. The standard way is iterative reversal. It's done in place, modifying the existing list without allocating new nodes.
How does that work? Sounds like you could easily lose track.
You need 3 pointers, prev, current, and next temp. You initialize prev to null and current to the head. Then you loop 1, store the next node before you change anything, next temp equals current.next. 2, reverse the pointer, current.next equals prev. 3, move forward, prev, current, next temp. Keep doing that until current becomes null. Your new head is the final prev.
Okay, carefully stepping through and reversing each link. That's O(n) time and O(1) extra space.
Exactly. There's also a recursive way to reverse a list, which can look more elegant code-wise, but it uses O(n) stack space because of the recursion depth, so it's generally not practical for long lists.
What about sorting? Arrays often use quicksort or heap sort. Do those work well for linked lists?
Not really. Quicksort relies heavily on efficient random access for partitioning, which lists lack. Heapsort also benefits from the array structure. The go-to sorting algorithm for linked lists is merge sort.
Why merge sort?
Because merge sort works by recursively dividing the list into halves, sorting the halves, and then merging the sorted halves. The merge step just involves sequentially iterating through the two sorted sublists and combining them into a single sorted list.
Ah, and that sequential iteration is exactly what linked lists are good at.
Precisely. Merge sort doesn't need random access. It achieves the optimal O(n) log n sorting time complexity and works naturally with the list structure. Implementing the split and merge operations efficiently on lists is straightforward.
Okay, now for the really hard part, concurrency. Multiple threads trying to read and write to the same list. Obvious race conditions if you're not careful with locks.
Absolutely. Simple operations like inserting a node involve multiple pointer updates. If two threads try to insert at the same place without locking, they can overwrite each other's changes, corrupting the list structure, leading to lost nodes or infinite loops. Mutexes or locks are the standard way to prevent this.
But locks have overhead, contention issues. Sometimes people try lock-free approaches using atomic operations like compare and swap, CAS. But these have their own demons, right? Like the ABA problem.
The ABA problem is a classic subtle nightmare in lock-free programming. CAS works like this. Atomically update memory location X to value B, but only if its current value is A.
Okay, seems safe. Check before you write.
The problem occurs like this. 1. Thread 1 reads value A from a pointer, for example, the list head. 2. Thread 1 gets interrupted before doing its CAS. 3. Thread 2 runs, it modifies the list, maybe it removes the node at A, does some other work, and then allocates a completely new node, which happens to get the exact same memory address A that was just freed.
Sure.
4. Thread 2 then puts this new node back at the head, so the head pointer is A, B, A, 5. Thread 1 wakes up, it performs its CAS. Is the head pointer still A? Yes, it is. The CAS succeeds.
Whoa. But thread 1 is now operating based on the old state, thinking it's modifying the original node A, when in reality it's messing with a completely different node that just happens to share the same address.
Exactly. The value, the address, is the same, but the meaning, the underlying object, has changed. This can lead to silent data corruption, use after free bugs, all sorts of nasty issues.
How do you even prevent that?
The common solution is tagged pointers or adding a version counter. You use some extra bits alongside the pointer address to store a tag or counter. The CAS operation then checks both the address and the tag. In the ABA scenario, when thread 2 reuses address A, it would likely use a different tag. Example, increment a counter. Thread 1's CIS would then fail because although the address matches, the tag doesn't.
Okay, that adds complexity but solves the ABA race.
Mm-hmm.
What about the memory itself? In lock-free code, how do you know when it's safe to actually free a node that's been logically removed, given that other threads might still be trying to access it?
That's the other huge challenge, safe memory reclamation in lock-free structures. You can't just free a node immediately after unlinking it because another thread might have read a pointer to it just before you unlinked it and might try to dereference that pointer after you've freed the memory. Use after free.
So freeing has to be delayed. How do you manage that?
There are several complex techniques. One is hazard pointers. Each thread maintains a small publicly visible list of pointers. It's currently hazardous to delete pointers it's actively working with. Before a thread can actually free a retired node, it must scan all other threads' hazard pointer lists. If the node's address appears in any hazard list, freeing is deferred.
So threads essentially declare, hands off these addresses for now.
Pretty much. Another approach is epoch-based reclamation, EBR. Threads operate within epochs. When a node is retired, it's put on a list associated with the current epoch. The memory manager only frees nodes from an epoch once it can guarantee that all threads have exited that epoch and any earlier epochs, meaning no thread can possibly hold a lingering reference from that time period.
Both sound incredibly complex compared to just using a lock.
They are. Implementing correct and efficient lock-free data structures with safe memory reclamation is extremely challenging, reserved for situations where lock contention is proven to be an unacceptable bottleneck. It's expert territory.
Okay, we have covered a ton of ground. From the basic node structure all the way to lock-free concurrency nightmares and XOR list curiosities, let's try to synthesize the performance picture.
If you just look at the big O complexity charts, it seems simple, right? Arrays, O1, access. ON, insert delete in the middle. Lists, ON access at O1, insert delete at ends or with a direct pointer for DLLs.
That's the textbook summary. But as we spent a lot of time discussing, the real-world performance, especially around traversal, tells a very different story because of the memory system.
That's the absolute key takeaway, that theoretical ON sequential traversal for a linked list. In practice, on modern hardware, it can easily be 10 times, 50 times, even 100 times slower than the ON traversal of a simple array or std.vector.
100 times slower, even though they're both ON. How can big O mislead us so badly?
Because big O notation measures the growth rate of abstract operations, like pointer, dereferences, or comparisons, as the input size n increases, it deliberately ignores constant factors, and crucially here, it ignores the very real, very large cost of memory latency.
It assumes each operation takes roughly constant time.
Yes. But accessing memory doesn't take constant time. Accessing data already in the L1 cache might take, say, 4 CPU cycles. Accessing L2 might take 10-15 cycles. Accessing L3 might take 50 cycles. Accessing main memory DRAM after a cache miss, that can easily cost 100, 200, even 300 cycles of the CPU just sitting idle waiting.
And arrays keep hitting the cache while lists keep missing.
Exactly. Array traversal. Mostly fast cache hits, maybe one slow miss per cache line, every 8 or 16 elements. Linked list traversal. Potential cadre miss on every single node, forcing constant slow fetches from main memory. The number of operations is O and N in both cases, but the wall clock time spent waiting for memory completely dominates for the linked list.
So the constant factor that big O ignores is massively different between the two.
Massively. The CPU is starved for data with the list, while the array keeps the pipeline full.
So the final verdict on linked list, when should you actually use them?
You use them when the O1 insertion deletion at arbitrary points, given a pointer in a DLL, or at the ends is the absolute primary requirement, and traversals or searches are relatively infrequent or performance insensitive, or when the ability to grow and shrink dynamically without large reallocations is paramount, and node payloads are large enough that pointer overhead isn't a cache killer.
Basically, when flexibility and modification speed trump traversal speed and cache efficiency.
Precisely. If you need fast sequential access, if you need random access, if cache performance matters, and it almost always does these days, you should strongly prefer contiguous structures like arrays, vectors, or maybe those hybrid unrolled lists, often combined with specialized allocators like pools or arenas.
We really went deep today, from data and next to cache lines, memory allocators, ABA problems, and epoch-based reclamation.
It shows how something seemingly simple interacts in complex ways with the underlying hardware and system software. Data structure choice isn't just about abstract algorithms anymore. It's deeply tied to hardware architecture.
So, thinking about that architecture, what's the final provocative thought for our listeners? If cache misses and memory locality are so dominant in real-world performance,
Does this mean that the future of high-performance data structure design is fundamentally about fighting for contiguity? Should we, as engineers, almost always prioritize structures that keep data physically close together in memory, even if it means sacrificing some of the theoretical flexibility or algorithmic elegance of structures like linked lists?
are we heading towards a world where things like unrolled lists or specialized arena-allocated contiguous blocks become the default, and traditional linked lists become a niche tool used only when absolutely necessary?
We're certainly seeing that trend. Look at data-oriented design, column-oriented databases, the increasing use of memory pools in arenas. The performance cost of cache misses is so high that the complexity of managing more contiguous structures often becomes worth paying. The question is, how far does that trend go? Does the classic linked list become an endangered species in performance-critical code?
Something for everyone to think about next time they reach for std.list, or its equivalent. A fascinating deep dive. That's all the time we have today.